Hi, my name is Steph Evans and I'm the lead FEA engineer at Evotech CAE Limited. This video, presented in collaboration with MSC Software, makes up a tutorial from the Apex 101 for Aerospace Applications series and is focused on a number of aspects of composite modelling and analysis within Apex. We're using the Harris Hawk release, highlighting key functionality using the composite tools. In this worked example, we'll go through the full process description for a working wing structure, focused on CAD to results with ultra-rapid ply output and update, highlighting numerous Apex technologies to allow fully generative composite FEA. This example is broken down into a number of key stages. Model build. So we'll look at CAD to working FEA model, highlighting direct modelling for 2D element idealization, with some automated property definition, followed by analysis readiness and model verification. Then we'll move on to Fastener automation, and that includes Python-enabled API and a script or macro which allows us to automate fastener generation based on the underlying CAD data, looking at hole-to-hole detailed joint response for any subsequent composite analysis. Once we've got the model built and tied together, we'll introduce the composite part definitions within the new functionality in Harris Hawk, and that will be based on a ply-based composite modelling and post-processing technique, respecting manufacturing principles, and with direct modelling allowing for generative laminate definition and update, ply updates, and some of the core sample stack verification tools. And then finally, we'll look at laminate modification and optimization, whereby we can use the direct modelling tools for ply and laminate updates and computational parts to allow us to turn around analyses very quickly to assess laminate response. We can look at the output on the fly using a mixture of composite failure theories. Okay, so we'll start off with this worked example in the composites tools within Apex in the full development of a wing structure. So bringing some CAD geometry from an external source, reading in Parasolid XMT file in this particular occasion, and we can see that the model browser tree is populated with an assembly that represents the full wing, and then sub-assemblies that represent skins, ribs, front spar and rear spar, color coordinated or color coded rather, to allow good visibility of what's going on within the structure. So if we put the wing skin into transparent mode, we can see the internal rib and spar definition, and you'll notice that each fastener is modelled explicitly as a hole within the three-dimensional CAD geometry. And taking the wing skin off, you can see the lightning holes and flange and stiffeners that represent the internal or the substructure supporting the panels. So this is looking at a 2D shell meshed idealization from a rib to rib, so a single bay definition. So we're looking at mid-surfacing with auto assign thickness turned on, such that the mid surfaces are generated and the three-dimensional CAD data that was used to generate to create those mid surfaces is stored as a thickness explicitly to allow us to define properties onto the FEA entities later on. So if we look at the rear spar explicitly, we have a number of surfaces or a number of mid surfaces created, and inspection of the region shows that we have a couple of areas of potential issue. So one of those is a fillet surface which we've deleted. Then we can extend surfaces. So currently we have a number of surfaces which are not connected. So using simply the extend surface function, based on the search distance of 20 millimeters, the edges are snapped through to adjacent surfaces, and we now have a series of free edges, shared edges and manifold edges shown highlighted in red, green and yellow respectively. So we measure the hole diameters first of all to allow us to guide the subsequent 2D shell meshing operation, and we're going to use feature mesh settings here. So this enables us to tailor the specifics of the meshed algorithm based on a particular diameter or particular dimension of a feature. So we're looking at washers in this case, and we've set a washer with a seed of 12 elements around the circumference and 1 element through the thickness. So meshing with a 5mm edge length, we can see the washer mesh definition at each hole, the thickness of the underlying property that again was used or generated as part of the 3D CAD definition, and then we can now start to look at detail, element quality, so live feedback in terms of the mesh definition. So we can see we have 0 invalid elements, 0 bad elements, a number of poor elements, but we're mainly dominated by good quality elements given the meshing algorithm that we've used. So again, defeaturing, 2D fillets around the 5mm ballpark, so it's picked out 2 fillets or 2 sets of fillets, just less than 5mm and one with 5mm explicitly, and that takes off the corner fillets or corner radii that was found on those surface edges. So tidied up the geometry nicely. We've got some potential issue with the local transition at the region shown now. We can use the vertex edge drag to manipulate the geometry, which in turn updates the mesh and in turn updates the element quality. So we've got live feedback in terms of what we're doing in terms of manipulating the model. Vertex edge drag is very straightforward to use, and guidelines are generated to allow us to follow particular forms, parallel edges, right angles, etc. So another change we're going to make is introduce a split into the surface near these edge holes, and then again checking the element quality, no bad or poor elements, so we're pretty good to go. Again, depending on how we plan to model the fasteners within this model or within this structure will determine how we mesh in particular local areas. So by defeaturing the fastener holes and creating a hard point, a seed point at the hole center, we can see we've got a very regular mesh if we wanted to use a node-to-node element connection. In this case, we're going to use what's called a hole-to-hole fastener definition. Thereby we want the fasteners modeled explicitly within the meshed entities. So checking surface normals first of all. Happy with the surface normals, we can flip things over around or check consistency if required. Looking at the element properties, similar to previous, however the properties have been maintained with all the surface edits and geometry manipulations that we've looked at. We can check model topology in terms of free, shed and manifold edges based on the mesh rather than the geometry. So that completes the rear subspar. So we're going to effectively repeat the same operation for a rib, just running through very quickly. A lot of the direct modeling tools within Apex make geometry to mesh or CAD to mesh almost a trivial operation these days, but we can very quickly mid-surface and extend those surface edges to meet adjacent surfaces to have one consistent surface definition. So meshing the full structure with again with the same feature mesh settings and an element edge length of 5mm, we end up with a nice ring of elements based on the feature mesh settings around the fastener holes. We're trying to be efficient with this model, so we've upped the element edge length for the shear webs with lightning holes in the ribs, again using the feature mesh settings for a bigger hole diameter, and remeshing we can now see that we develop washers around the holes and a much cleaner definition, certainly in the areas away from the fastener holes. Okay, we're now going to defeature again. Again, similar to the rear subspar that we just looked at, but picking out the fastener holes and again defeaturing on the fly, creating seed points at hole centers, and the geometry is updated with the mesh very quickly. And again, we can use this definition for a node-to-node fastener representation if we so desired. But again, in this case, we're using the hole-to-hole approach, so we're going to undo that defeaturing step to allow us to return to the original definition. So checking the element quality now for the full meshed substructure, and we can see we have a number of invalid elements. So we can use element quality to isolate the area of poor elements. So we see the poor elements along with the associated geometry, and again using the direct modeling tools we can effectively understand what the potential issue is in the given region. And again here it looks like we've got a quad with a very small edge length, so simply moving one of the vertices out of the way, then snapping it back into the T-section, and the element quality is updated, and we have no invalid elements left in the model whatsoever. A very small number of bad elements, but massively dominated by good quality elements as a percentage of the overall definition. And bearing in mind that the element quality around fastener holes is controlled by that washer that we had set in the feature mesh settings. So moving on to the panels, or the skins, the aerodynamic skins on the wing structure. So this time we're mid-surfacing, but we're actually extracting surfaces on the outer mold line, or the outer mold surface of the geometry, to reflect the manufacturing mold surface when we get into looking at the composite properties. So modeling, or rather meshing the resultant surfaces with a quad only mesh and a 12.5mm edge length, and we can zoom in. We've got the washers where required, but you can see there's a pretty poor mesh definition elsewhere. So again, one thing that we may possibly look at is node-to-node fastener. Obviously not in this example, but a quick defeature shows that we now have very regular surfaces, and the hard nodes defined at hole centers. We can see that we've got a near perfect quad mesh for the whole of the surface structure. So just undoing that, putting the holes back in and deleting the underlying surface mesh, we can start now to break up the panels into what we'd call a fine, a transition, and a coarse mesh region. So we're going to do that with some of the direct modeling tools, but in this case we're looking at using a sketched surface and to develop some geometry from that sketch surface to allow us to break the panels into the discrete regions that we need for the resultant transitioned mesh definition. So once we have a sketch surface defined sort of normal to the bottom of the wing, we simply pick the edges of one particular panel of interest. So we're just selecting the surface, selecting the edge. Once we've got those defined, it's simply a middle mouse button to accept, and we can see when we max the view that we have a single surface left behind that's cut, which is effectively a projection of the edges of the wing surface projected onto the sketch surface. So we can push-pull that surface up to develop a 3D piece of geometry, and what we're going to do is manipulate this 3D geometry to give us the cut surfaces that we need for the wing surface manipulation. So we're going to shrink the overall three-dimensional solid based on push-pull and a negative 40 dimension or shrink in the surface normal direction, and then we're going to simply hide the surfaces, hide the solids I should say, pick the surfaces that we want to split, and then put the solids back in view and use the split surface tool to highlight the faces that we want to split the underlying wing surfaces about. And again, by hiding the surfaces we can see the splits with the green shed edge lines that we wish to split the surface about. So again, just skipping a couple of mouse clicks here, we've shrunk the solid again, the red solid, the cutting solid that is, and we've split the surfaces once more, and now we have three zones defined, or three patches defined for the overall surface to allow us to use our fine, transition and coarse mesh definition. So we remesh the fine region with a 5mm edge length, a quad only with a matte mesh. If you were to focus on the holes, you can see there's the washers with the nice regular washer definition defined. We can mesh the coarse region with a 20mm edge length, and then the transition region with a 10mm edge length to transition from fine mesh detail where we need it around the fasteners, but to course elsewhere, still maintaining good element quality and minimizing the overall shape or the overall size of the model. So again, just repeating those 3D surface cuts on the underlying wing skin geometry or wing skin surfaces. Similar approach to what we just showed. Skipping the mouse clicks, and again hiding the solids, we can see how we've cut the rest of the surfaces as well. So showing the whole of the geometry and the mesh that's defined, we can zoom in into the fastener regions and show we've got a very nice, well controlled and very quick to create mesh definition for the full single base structure, both for the ribs, spars and for the skins. So now we need to tie the structure together. So we're going to look at some simple fastener creation techniques. Again, first of all, we're going to defeature all of the holes from the entity shown on screen to generate a hard point at hole centers and a very regular mesh, a very regular quad mesh defined at the fastener interfaces. So just run through the defeature operations as seen, and then if we zoom in onto in this case a rib to front spar definition, we can see the hard nodes or the hard points that have been created, and we go into the connector toolbox, and in this particular example we're going to look at rigid connection. So it's a manual approach in this instance to pick one node at one end and the other node connecting to the ped geometry to give us our fastener definition. Okay, so that's a very straightforward way to create the node-to-node connection. So we're going to undo the defeaturing operation and generate the holes back in the structure, again with the rings around the fastener to give us our good quality for result output later on. So this time we're going to look at a flexible connector of fastener definition, and we're going to use a surface edge for one part, surface edge for the next part, middle mouse button to accept, and what that does is it creates an MPC equation in one hole, MPC equation in the other hole, and then a beam element, or a bar element which connects the two entities together. Now that's straightforward to do, but in our model we've got upwards of 240 discrete fastener pairs for what is a relatively simple structure, but obviously it's going to be very difficult to do that on a manual basis. So we just showed some Python script there that's been developed, which basically looks through the structure, finds hole edges, generates points at those hole edges, and then does a proximity search to understand which entities are connected to one another, and it then automates the MPC and bar element generation for the full structure. As you can see, it then gives a summary of all the surface pairs and the number of fastener elements or fastener definitions it's created. So a very effective way of working with the model using a Python script, and again pretty straightforward to run and can be manipulated pretty much for any particular type of model. The material properties that have been defined is an Inconel alloy, which we define within the script based on the modulus and shear properties for the material. So once we have the connectors defined, you'll see that in the model browser tree, each connector is named by the component A, component B contact pair. So we can see by showing the rib to skin fasteners by highlighting those in the model browser tree, and then showing the rib and skin entities, we've got the fasteners defined solely for that joint definition, and we can modify them if required. So before we get into the composite model development, we're going to look at some basically analysis verification to be sure that the model runs as expected. So we've just done a simple free analysis using the embedded solver within Apex, and into post-processing we can look at the deformed shape for a given mode, and then if we plot the mode table, we can see that there are in fact 6 rigid body modes for the free analysis, and then mode 7 plus are elastic body modes, exactly as as expected. So we're good to go in terms of the model connectivity and mesh definition and properties for the bulk of the region. We're now going to look at composite modeling and analysis, or composite part definition. So to simplify the model browser, we've created a new part, or a new subassembly called skin detail. And for the large rectangular skin, we're going to move the surface and meshed entities into that subassembly. That will give us benefits in terms of post-processing and some model manipulation downstream. So we need material properties. So we've just run a simple script that we have created for a T800 weave 2D orthotropic material, and we can see here we've got moduli in 2 directions, shear modulus, in plane, out of plane, Poisson's ratio, density, and stress limits for tension and compression in both directions and in plane shear. So it just saves a number of mouse clicks by having that information stored in a script, and again it highlights some of the benefits of automation through the Python API. So now we have a material to work with. Again, looking at the skin detail panel of interest. So go into the attribution tools and select the panels function, and we can specify a surface where we want to define the composite properties. So we define a name, or we give it a name, in this case the same as the subassembly for ease of model manipulation. And we can see that we have the panel which turns yellow, so we've got the full extent of the surface. We have a pinkish vector shown, which is the build direction. So if you think of the yellow surface as the mold tool for composite manufacture, it controls whether the plies are built into the structure or away from the substructure. Again, we can define an offset if required, just shown there on screen, but in this case we have no physical offset because we've modeled the mesh at the surface outer mold line rather. So we want to align the material orientation for the laminates that we're about to create such that the x-axis is aligned in the spanwise direction. So any subsequent plies defined in the 0 degree orientation will have fibers running parallel with the spanwise direction. We're using a woven cloth, so we have fibers in both warp and weft, or x and y, but we can accommodate the orientation vector as needs be. So again, we can see the red vector shown on screen highlights the 0 degree orientation. So this slide demonstrates, or rather specifies, a very simple layup ply book that we may have had from an initial design or from manufacturer, and it shows that we've got 3 zones defined. Zone A has 7 plies in a 0.45 symmetric stack. Then we have Zone B with 5 plies and Zone C with 3 plies. Again, we're using a 1mm ply thickness, so the image on the right shows that we have 7mm in the outer zone, 5mm in the transition zone, and 3mm in the intermediate zone. So it's again straightforward to specify the zones and subsequent ply definition to allow us to mirror the ply book that is required from initial design or from manufacture. And you can see the mold surface given, which is effectively the surface geometry that we've selected for the outer mold surface through the use of a panel. So now on the panels form we can switch into the plies tab. So to create a ply we specify a material, a thickness and an angle. So again, T800 weave, 1mm thick, and an angle of 0 degrees. We can specify the whole surface or faces within the surface. So turn the surface back on for visibility, and we're picking all 3 faces that make up the surface based on those splits that we did previously. So we create the ply, color coding the plies such that the 0 degree plies are shown in blue, and again we can see the orientation vector, the 0 degree axis. We're going to repeat the process now for a secondary ply, or the second ply on the stack. So we're building plies up from the mold tool. We can shuffle the stack around later on if needs be, but by default it works from the mold surface and moves up in the direction of the surface normal. So again, picking a second ply, again same coverage but this time with a 45 degree orientation, and we're specifying that with a yellow colour to highlight it or to separate it from the blue ply. And then we just work through to reflect what we anticipated in the, or what we were provided in the ply layup definition, and we can see we're working through, and we now have a number of zones generated based on the plies as we create them. So again, very straightforward, and we're not picking FE entities or anything like that at this stage. Simply selecting the geometry. The generative nature of Apex means that these ply definitions are washed through to the underlying mesh definition, but we don't need to worry about that at this level. So you can see we've got 3 zones defined. So zone 1 is the coarse mesh intermediate zone, zone 2 is the transition zone, and then zone 3 is the fine mesh outer zone. So we've got a thicker laminate in the outer portion and thinning down as you come to the center of the panel. So looking at the zone definition that we've just defined through the use of the ply layup, we've got the original laminate definition requiring only 3 unique zones, shown red, green and blue in the right hand image. This then translates into 3 underlying pcomp, so pcomp or pcomp-G property set. So if we to write the deck out, we can see those pcomp-G cards defined. And then working on a zone by zone basis, if we highlight the plies in the lower box as shown now, you can see the ply coverage, the colors of the plies, and again we've color coded them, and a graphic showing whether it's a 0 or 90 degree depending on whether we have well, on our layup definition. So again, very easy to visualize what's going on with the plies on the given zone level and for the full laminate. So if we come out of the ply tool, or the panels tool I should say, and then double check the laminate thicknesses, again we can see the offset. So we've got staggered thickness from 7mm, 7 plies on the outer face, through to 5, through to 3mm. We have an additional tool within Apex that's new within the Hawk release, in that sense that we can do core sampling. So we can effectively select a surface face, a zone, or even an element, and we will then see the core layup defined through that surface. So again, red, green, blue, so going down 7 plies, 5 plies, 3 plies, and it gives us the ability to view the layup, but also we can modify the ply and the ply layup from the core sample tool. And again, we'll just show that quickly on screen. So we select the icon from the top right of the toolbar, pick one element in the thicker region, 7 ply region, and we can see the 7 ply shown in the display, and we've got a graphic showing the 0 and 45 degree, and we can cycle up through those and double click on any ply if we wanted to modify or edit those plies accordingly. So we have our initial laminate defined as required. So the next thing we're going to look at is to run an analysis with the embedded tools or the embedded solver within Apex. So pretty simple in this case, but we're just going to put a simplistic wing bending load onto the structure. So on the inboard rib, we're simply fixing or clamping in all 6 degrees of freedom the edges which make up the boundary between the rib web and rib flanges, and the whole perimeters as well. And then in terms of load application, so we need to define a position where the load will be applied. So we're going to select one of the lightning holes and create a node at the center of that hole. We're going to use a standard technique, the shear moment and torque technique, or SMT technique as it's sometimes known, whereby we can specify, or rather use an MPC type approach, or rather distribute the load through a series of structural entities. So in this case we're going to highlight the interface curves between the flanges and webs, and then use the distributed load type, again, which is basically an MPC type equation under the hood, RBE 2 or 3 depending on what's required, to act so that the load acts at the node at the center of the hole, but then the load application is beamed out through the MPC to act on the shear web to flange interfaces, as is typical wing bending wing box load application. So defining some span-wise and vertical load to induce our wing bending action. So once defined, we can just highlight, or rather show the whole model structure, and then move into analysis. So we've run a verification analysis so far, but now we're going to run through analysis readiness, and there are no issues with the model, so we know that the panel or the laminate definition is appropriate. For laminate analysis, it's useful to include, as well as the default output request, sometimes having laminate strain, so that the homogeneous strain output can be useful in understanding what's happened with the structure. So run the simulation and into post-processing, and then we can start to look at the behavior of the structure and how the laminate has behaved. So again, looking at the scale deformation, obviously a huge scale factor on this output, hiding the composite panel of interest, and then looking at displacement, animating that displacement, and we can see the wing bending action. This is actually a down bending case, so it's going to put the upper wing skin or the panel of interest into tension typically. The large displacement is mainly due to the laminate offsets and the use of the pretty thick plies that we're looking at for this example. So we can see we've got various outputs, so we can look at element strains. So we're showing strain von Mises for the homogeneous top and bottom skins. That's a good marker of understanding what's going on. We're going to focus the post-processing on the skin detail. So by double-clicking on that particular sub-assembly within the structure, all subsequent post-processing will occur just on that entity, and that's useful in terms of any fringe plot output will be reflected, or will be apportioned based on what that particular sub-assembly is doing, so you're not skewed by spurious output from elsewhere. So now we can start to look at strains, max principal in this case, show the principal vector or the principal tensor directions for principals, and we can see we've got tension developed across this fastener interface, and that's borne out if we animate the structure, because the panel is doing the bulk of the load transfer between the rib and the front spar. So there's no surprise that we've got a high strain or a high load going through that region. So once we've made a sort of global assessment of the panel or the laminate response, we can start to look at the composite failure information on a laminate or rather a layer or a ply-based approach. So we're going to use ply-based output in this case. We're looking at a max strain in X failure criteria for simplicity. There's all sorts of different criteria that we can use if necessary. And looking explicitly on the failure indices, we've got a failure index of 1.6, which exceeds a value of 1, which shows that we have a ply which has failed within the laminate. So we can use the hotspot display to show us where that output is potentially causing a problem, and then we can look through the ply definitions on a ply-by-ply basis, and as we click apply, the output is updated on the fly, and it's very easy to see the laminate response and understand which is the critical ply or plies within the stack. So once we've got the output display to screen, a very useful technique at this post-processing level is the ability to use the core sampling tool that we looked at earlier, and basically we can understand the layup and relate the result output to what we're seeing in terms of the stack, which gives us a much better diagnostic in terms of the overall structural behavior. So with the initial laminates defined, we're now going to look at some laminate modification and potential laminate or ply based optimization to hopefully bring the failure indices down to a level that we can live with in terms of this structure. Of course, we're using idealized laminates, but it demonstrates the process. In many cases, we have a much more complex ply definition. Okay, so similar to how we split the panel of interest for the mesh transition, we're going to use a similar technique to split the split the underlying panel to allow us to define some patch plies to strengthen the regions where we saw potential failure earlier through the original laminate. So a simple case of picking the panel, picking the surface of the 3D cube or 3D shape that we've got access to, and then we can basically chop the panel up. The mesh is updated automatically, so we've got a single patch defined at the moment. So we're going to shrink the underlying 3D entity by 50 mil to give us our new patch definition. So again, pick the panel, pick the face where we want the split to take place, and then repeat that all the way around the composite panel or composite geometry to give us a series of split surfaces or split faces that we can now define our patch plies about. So we just repeat that for the full process, and we can now turn the solids off in the viewports, and we can now see the shared edges, which we're now going to use for the new patch ply definition. Okay, so if we look at the mesh, we can see as we've split the panel, it's taken some of the master mesh definition from the fine mesh region. So we just need to quickly remesh the coarse and fine locations using the standard hybrid and auto meshing algorithms. So using a 10mm edge length in the transition region, we can quickly go around and update those to get much better quality in terms of the coarse to fine mesh representation that we're interested in. And again, if we hide the surface from view and turn off the panel display, there's lots of entities on top of one another, which sometimes busies the display. But we can turn entities on and off in the browser. So we can double check the element quality, and we have no invalid elements. So we're good to go in terms of the panel definition, or the mesh and geometry target, to allow us to update the laminate and define the patch plies as required. So just before we get into the laminate definition, we just double check the thickness, and we can see because of the generative nature of Apex, we've maintained the surface or the shell properties even after we've split the geometry and consequently updated the mesh. So it saves, or rather the generative nature saves huge amounts of time in terms of model update. And again, we can double check that for the fasteners. So there's been a remesh, but the fasteners being generative have understood that remesh and updated accordingly. And that's worked very nicely for what we're trying to do. So if we just look at the panel and the underlying surface, and again we still have the original panel definition defined with the 7 plies for the outer region. So what we're going to do now is create some new plies which are defined in the sort of forward corners of the panel where we had the load path and the maximum failure indices seen. So a quick ply created in one of those corners. Again, T800 weave with a 1mm thickness and a 0° orientation. And repeat that on the other side. As we build these plies, we're color coding them so we can recognize them very easily in terms of where they've been defined through the core tools or through the display within the stack. And again, so creating a slightly bigger patch ply in the corners, and again same material, same thickness and a 0° orientation, and again updating the colour so we've got a good understanding of what we've done with the plies for later on. And again we've got the same plies defined from the original laminate, so we can just cycle through those to show the 7mm down to 5mm down to 3mm, but of course now we've got the 2 pairs of patch plies on the outer surfaces. Now one thing that's apparent here is that just the simple addition of adding 4 patch plies has ramped the number of zones up dramatically. So again, this slide highlights this quite nicely in that the laminate or the panel display shown in the main image, we've got 19 zones defined, and if we look at the color coding on the right hand image, you can read across to how those new properties have been defined on the structure. Now 19 zones for 4 plies is difficult to work with. They can be rationalized into 10 zones based on the symmetry in the structure, but traditional techniques, so what we'd call a non-Apex FE based techniques, where we're not working at a ply level, the effort involved in defining those new property sets as you introduce additional patch plies increases exponentially, and it becomes very difficult to work with plies on a legacy system using a non-ply based approach. And again, if you write the deck out, you can see that the reams and reams, well, in fact 19 discrete patch plies or discrete P-comps that have been created to reflect the original laminate with the patch modifications that we've just made. So again, we can look at the 3D thickness, and again we now have the 7mm with 2 plies on it, so it's gone up to a 9mm thick definition in the corners where we want the additional material. And again, using the core sample tool, we can see the color coded new plies as they've been defined, and we can cycle through the core sample to show the extent of the ply. So a very nice way of working with both composite laminate definition, modification, and we're about to see some of the post-processing as well. So going into simulation, now bear in mind that we've already run this model once, then the only change is the composite panel. So Apex has stored the computational parts, meaning that the analysis runs through very quickly. So we've got a very rapid turnaround in terms of seeing the effect of our laminate update. And again, going into the post-processing mode, we can see the overall displacement of the panel and substructure. So taking displacement off, highlighting the skin detail, so the fringe plot is tailored specifically to that region, and going through to composite failure, specifically into the ply based output, showing all plies, and switching the switching to the appropriate output, and we can now see our failure index has reduced from 1.6 to 1.01. So we're right on the knuckle in terms of the output that we wanted. So we've got a working structure. So again, a quick way of demonstrating how we can make a modification to a given laminate. Okay, thanks for watching this tutorial, and I hope you found it both informative and interesting. I'd like to say a quick thank you to Larry Pearce and Stefan Ternelius of MSC Software, who helped out with the generation of the Fastener automation macros. Be sure to keep an eye out for the remaining tutorials in the 101 series to illustrate how Apex can help with your FEA process.